Hi, I'm Cheng. We are the team from the University of Edinburgh. I'm gonna present our recent work, Visually Interpretable Subtask Reasoning for Visual Question Answering. So, what is visual question answering? It asks the model to answer a question about an image. Recent multimodal large language models like Lava and Vita are commonly used for this task. They are often trained with instruction like, please answer the question in a single word or phrase. However, under this instruction, these models typically offer no visible reasoning and no visual explanation, makes their decision process hard to interpret. To address the lack of explanation, we can prompt MMMs under this instruction like, please explain in detail. It's like a chain of thought reasoning. As shown here, the model gives a much longer response. While this improves explanation, but there's still no visual evidence. We don't know where the model looked, and no explicit, verifiable reasoning steps. One way to make VQA more interpretable is through visual programming. It solves complex visual tasks by breaking them down into simpler interpretable subtasks. These subtasks are generally like Python codes, which are executable, such as object detection, comparison, or spatial reasoning. And most of these steps are associated with pre-trained models, so it's verifiable for each reasoning step. However, they rely on executing multiple specialized models, which can be computationally expensive, inconsistent across datasets, and prone to execution failures. So, for better interpretability and reasoning ability of MMMs, we propose a visual interpretable subtask reasoning framework. So, given a query like what kind of animal is in front of the truck, we decompose the problem into subtask sequences. So, these subtask sequences provide trustable textual reasoning logical and object-level visual explanation for MMMs, which is called subtask of thought. Via subtask of thought, we could provide explicit reasoning through instructions and also visual explanations. First, the problem here is how to get the subtask of thought datasets for the next step training. Given QA pair and scene graph, which provides object relationship in an image, and predefined subtask and sequences from GQA like this, we prompt Llama 3.1 70 billion to generate subtask of thought based on in-context learning. After generating lots of subtasks of thought, we do instruction tuning on Anvila 8 billion with instruction like, please explain the rationale by decomposing into subtasks to answer the question, so that the model could generate structural, texture, and visual explanations during inference. In terms of the experiments, we do experiments of accuracy across some compositional VQA datasets. In Table 2, our model achieved a new state-of-the-art performance on the GQA test dataset. Additionally, we conduct a zero-shot evaluation on the correct dataset, which is a compositional reasoning and common sense dataset. As shown in the Table 3, the result is better than the backbone model, which proves the generalization capability. In terms of interpretability, we first evaluate the quality of textual rationales generated by our model compared to the back model. For NVIDIA AB, we prompt the model with the instruction like, please explain in detail during inference to obtain detailed explanation. Because these explanations are open-ended, we evaluate them based on semantic similarity between generated explanations and ground truth answer, which is shown as answer accuracy here. And for operation accuracy, to ensure a fair comparison, we evaluated without arguments of our model's predict subtask of thought with the ground truth annotations. It specifically measures whether each reasoning step, like operation prediction, aligns with expected subtask operations without considering detailed arguments. And for logical accuracy here, we measure the logical accuracy where the overall reasoning process logically supports the final answer, considering the operations and intermediate results. So here, as shown in the table 4, it demonstrates that V-star outperforms on textual and interpretability across all metrics compared to NVIDIA AB. And on top of the textual interpretability, we evaluate the performance over visual interpretability. Here, we assess the accuracy of our object-level bounding box prediction. Since NVIDIA AB does not generate bounding boxes for VQA, to obtain them from it, we first obtain its predict answer using the original VQA instruction, answer in a single word or phrase, and then append a follow-up instruction from its object grounding task, provides the bounding box coordinate of the region to extract the corresponding bounding box. For our proposed model, we extract the bounding box of the final answer. The comparison is based on IOU. V-star consistently outperforms NVIDIA AB in both answer correctness and bounding box accuracy based on IOU. We also perform evaluation studies to analyze the contributions to interpretability by removing different components in subtask of thought. First, we test the role of bounding box for visual explanation. Removing them leads to a drop in IOU from 48% to 44%, showing their importance for spatial grounding. Second, we examine the impact of shown interpretability intermediate answers during reasoning. We checked if operations and the arguments match the final answer. When the answer is correct, the steps are usually correct too. But when the answer is wrong, we find that intermediate steps also tend to be inconsistent. There are some demos during human evaluation. As you can see, there are some errors like it detects one correct object but missed others, or it swapped a subject on object like saying wearing girl instead of girl wearing. For taking away, current interpretable words are trying to interpret the model, but when the model makes mistakes, it's better to refine them. And recent work on interpretability, it also challenges to evaluate the interpretability automatically without the ground truth.